Hi everybody, I'm Samir from Stony Brook University, and this is a joint work with a PhD student Mallesham, who is here. So all the hard questions go to him. And we are fairly new in this sort of work, video streaming on wireless, and this is also a work in progress, so the feedback will be appreciated. There's nothing published yet, but this is a good application. This is once again an application like the previous presentation, Malati's presentation. There's nothing to do fundamentally with wireless, but we have an interesting idea about how to exploit the edge cloud. So the topic is panoramic video streaming. Panoramic 360-degree video streaming is popular. Most of you, all of you have seen that or experienced that. And the idea is basically, giving you an immersive sort of feeling using the picture is taken by a 360-degree camera, which shoots picture in all possible directions, and then the image is projected over another plane to make it suitable for viewing on a two-dimensional display device. And there can be a lot of different mechanisms for this projection. There are a few popular ones like equirectangular rather, cube, pyramid. It's not very relevant for my talk. We used equirectangular because it's kind of simpler for our technology, but it is kind of tangential. And then this image is expressed into multiple bit rates, and then it uses the more or less conventional video streaming, any standard ABR protocol to stream. Depending on the network bandwidth, you see the appropriate bit rate, appropriate quality. So that is basically the overall idea. So the challenge here, as you can imagine, is that the image is surround panoramic 360-degree video, but the player or the viewer is going to see only part of the image, obviously, according to his field of view, which obviously is a problem because you now need a lot more bandwidth for the same quality. You'll be seeing only a part, but you have to stream the entire content. Okay, so that is kind of obvious, and that is a problem everybody is aware of, and a lot of people are working on this. So the current solution pretty much is focused on some sort of prediction. So you predict what you are going to be looking at, and this is based on multiple mechanisms, based on head tracking. So what your history of your head tracking is, what you have been looking at, you are likely to be looking at in a similar direction. And also, more recently, we have done some of this work as well, using computer vision techniques to model visual saliency, to somehow or other predict your attention, given your history, given the nature of the video, predict your attention in future. And this technique has a promise. So there's a bunch of paper published in the last couple of years. We also have an IFIP networking paper this year trying to do this sort of prediction. But if you look at the state of the art, the prediction, as you can imagine, is progressively weaker for longer time horizon. Obviously, you have to bring segments in future and to predict with a longer time horizon, really. But in our experience, it gets poorer beyond a second, and beyond 3 seconds is really bad. However, there is scope of improvement. So that is the way things are at this time. So we want to exploit a couple of new opportunities. So one opportunity here is using super resolution methods that has been known in computer vision world for a long time. So the idea here is like magic. So you use a low resolution image or video as a source and kind of hallucinate details to produce a high quality image. Okay, like something like that picture. Okay. So it looks really like a magic if you look at these pictures, the way things work. If you look at the input and output, it is amazing. But the ideas are not new. It goes back to the 90s. It is some form of interpolation using features present in other parts of the same image, or if it is a video, there is obviously a lot of redundancy because similar frames are being repeated, and use other frames, same feature in other frames to reproduce a higher quality image. And now, recently, there's a lot of interest in this because you can now use deep learning to do things much better. And if you look at the computer vision world, ICCV, CVPR, there are always few papers doing super resolution using deep learning. Our idea is to exploit this. Basically, obviously, there is a lot of opportunity here because you actually send lower quality image, you get back high quality. Particularly if your data is huge, then essentially it gives you some way to compress the video. And the downside of this is that it requires significant computational power on the client side because at the end of the day, you have to run a neural network in real time to predict the frames, basically. Now, however, there is opportunity because the GPU performance on the clients are improving. Particularly, if you look at the history of mobile GPUs, there is about a factor of 2 improvement in performance over the last 10 years. Also, there are new things coming up, this neural processing unit, AI core, which can do neural network-based prediction much faster. So the idea basically is to exploit these opportunities to do video super resolution. It may not be effective everywhere. Wherever it is effective, we want to do that, particularly for panoramic videos. You can do that for common video, normal video as well. There's actually a paper in last year with SDI doing for regular videos, but obviously opportunities are much higher if you go for large scale, high resolution 360-degree video. There are obviously a lot of details I'm skipping here. That is not really the intent of this talk. You need to figure out how to do the training. You need to think of the neural network model size. If the model size is large, then it defeats the purpose because you have to download the model. Instead of the actual video, you'll be spending time in downloading the model. How much you want to upscale the video, what quality is good for you. And also at the end of the day, the important thing is the latency. Even if you have a fast GPU, you still need to spend some time to generate the image, and you have to do that in real time. So we have an approach here to solve. The approach first does viewport prediction, kind of the same thing I pointed out to you earlier. And the way it is done is kind of conventional literature. In literature, you split the video spatially into tiles, and then predict the viewport for the next segment to be fetched, let's say this. And essentially, it is not a kind of binary. The prediction, it gives you a probability distribution at the end. So this is highly probable, and this is less probable. These other things are much less probable. And we use that distribution for our actual protocol work. That will be the next step. The next slide looks a little busy. But the essential idea is now that once you understand what these probabilities are, where you are more likely to look at, where you are less likely to look at, you figure out what to do with all these tiles. Basically, you trade some of the network for computation, in the sense that if your network is not good enough to deliver all these tiles in very high quality, you could choose alternatively to generate some of these tiles locally using the super resolution approach. So partially you download, partially you generate, and you do that based on the capacity you have. So the idea basically is, once again, there's lots of variations are possible. This is one of the ideas that we worked on and evaluated, but not set in stone because this can certainly be refined. So the approach is that you come up with a model of quality of experience, and here you can borrow liberally from existing literature. And these things are kind of standard now in video streaming, that how to model quality of experience. And here the only additional thing is that you have to factor in view probability. If some tiles you are less likely to view, you don't really care about that much, okay? Because the probability that you are going to miss that is very little. And then you optimize that model, the expression of the model, to determine exactly what you want to download and what quality you want to download, assuming multiple qualities are available, and which tiles you want to generate locally. Obviously, generation is not free. You pay some price in terms of computational latency. Also, you have to download the model and the low resolution counterpart, but that overhead on the network is very minimal. And sometimes you completely ignore. You don't generate or download either because you probably are not going to look at them. And obviously, there's a constraint here that you constrain the network capacity. Depending on what you choose to download, it has to fit within the capacity at that time of the network. And also, whatever you choose to generate, you should be able to do that on your GPU. The good thing about this work so far is that a GPU is a mobile with some constant capacity. That's the only thing that is doing this prediction. So we know exactly what the capacity is. And this can be potentially integrated in an existing ABR algorithm, and that's what we did so far. It requires some work, but it's possible. So overall, the techniques kind of look like this. You do some offline training to generate the super resolution models. And then the server has this low resolution version of the image, or the tiles rather, and also the models. And also it has the HEVC encoded tiles that is the same as the regular video streaming. And the adaptive bitrate control, we have a variation of a protocol that has been widely used in the community called MPC. You figure out if you want to download or generate, and then what is the bitrate you want to select for the downloaded tiles, and what is, and then schedule. If you want to generate, you schedule the generation of these tiles. And then they all come together and you put them together in the playback buffer. And obviously there are inputs to this, the predicted viewport, and what is your estimate of the network throughput is, what is your compute capacity is. This sort of is working well so far. We have some preliminary results where we did not do any user study yet, but there is a video data set available for the community, which has a number of videos with users with head tracking data set. Which is a pretty good data set for us to use. And we emulated the network based on the FCC provided broadband data set. And then Mallesham has an implementation, end-to-end implementation, which he ran. And it turns out, obviously, it is doing much better. This is a CDF of some expression of the quality of experience. Our system is called PARSEC. And this is doing much better than all competitive techniques we can think of. The other plots are, there's a system called Flare from last year's Mobicom, which does viewport prediction with ABR mechanism. NAS is a video super resolution technique much like ours, plus ABR, but assumes regular video, doesn't do anything special for 360 degree. And VP only does VPR prediction, viewport prediction, but no ABR. And obviously we are winning because we are taking care of, you are putting less burden on the network, and so the network can bring in more higher resolution tiles, and the other part you are generating locally, so you are getting something for free. So it's obvious that this mechanism will do better. So now the problem. Okay, and everything looks good. The only thing that I did not tell you so far is that so far we used for all these things that we did are desktop class GPUs. They are obviously much more powerful. And here the experience shows, and if you just focus on this part of the plot, that quality of experience is better as you go to like better CPUs, which is kind of obvious because you are getting a lot for free by exploiting these GPUs, by generating these tiles sort of magically on your mobile and downloading only very little. But we get into trouble when you use mobile GPUs. So Mallesham experimented with Pixel 3 and OnePlus 6. They provide somewhat subpar performance. It's not quite out there. I don't have the data here. And also one of the problems is that there is an excessive energy consumption now. Okay, because it's always running this neural network on the GPU. And obviously it's not very realistic for you to do. So suppose you did not do the super resolution versus you do the super resolution. With super resolution, there is about 43% higher energy consumption, which is kind of expected. So one idea here is that until GPUs catch up, and even if GPUs catch up, the videos are going to have more and more resolution. So obviously there is more and more demand on this GPU and the network. And particularly in the context of Cosmos, we want to explore edge computing. Okay. So the idea there would be is that this tile or frame generation part, we want to schedule on the edge cloud, okay, as opposed to doing on the mobile. And hopefully the edge cloud is going to give us a large number of GPUs to do it very fast. And I also noticed that there is an FPGA This is the chart I borrowed from Cosmos website, okay, which tells us that there will be FPGA there, so which gives us an opportunity to have programmed FPGAs to do these neural network predictions. Now we need to modify the bitrate adaptation that we will develop that will adapt to both of the network throughput as well as the edge computing capacity. Interesting thing now on the edge will be that the capacity will be variable. It's not constant because the edge will be doing other things and not just our work. and that could be multiple processors, small number of processors. So depending on the availability, so the ABR will have a new twist. It's not adapting just to the network, but also the edge capacity. And we need to develop, of course, the appropriate protocol support from the edge and the device. As I said, that we are really interested in using FPGAs on the edge for better speed. We actually have several faculty who collaborate with us who are experts in doing neural network on FPGAs. There is also some scope of distributing the computation split the computation in the mobile and the edge, depending on the latency and other issues. And also, obviously, these are all very latency sensitive because now you are going to generate the frame on the edge, you are going to display on the mobile, how the latency is going to play a role, we don't know. And these are obviously something of interest to evaluate. And that is basically what I have. I'll take questions.